Hi, I'm Becca Reisman, and I'm a project engineer at the Aerospace Corporation. Today, along with my colleague Jamie Wilson, we'll be discussing the physics of space war. Recently, there's been a lot of talk about conflict in space. Many things have contributed to this, including the reestablishment of U.S. Space Command, the creation of the U.S. Space Force, and probably also Steve Carell's Netflix show on the topic. So, what Jamie and I decided to do was to write a paper on the physics of space war, or specifically space to space engagements. As there is more talk about the policy and strategy on operations in this domain, we thought it would be helpful to add to this conversation. The way in which things move in space is not intuitive to most of us, and so we thought this would be helpful. This video is a summary of that paper. Note, this is neither a discussion on strategy nor a comprehensive overview of counter space threats. To help set the stage, it's important to recognize that conflict in space will look very different from conflict as we know it on Earth. It will also look very different from the space fights that we see in movies and TV shows. Space fights from things such as Star Wars actually resemble the movement of airplanes, but the physics of space would not allow for that. Furthermore, conflict in space probably will not involve humans, at least not anytime soon. For the time being, humans are sending people into space for science and exploration, and possibly tourism. However, the Space Force does not have astronauts, but it does have satellites, and so that brings us to the physics of satellites moving around Earth. There are 5 key points to keep in mind throughout all of this. First, space is big. This seems like a pretty obvious statement, but it's still really hard to comprehend just how big it is. The volume of space between low Earth orbit and geosynchronous Earth orbit is about 50 trillion cubic miles, or about 190 times the volume of Earth. Second, satellites move quickly. In commonly used orbits, they travel anywhere from between 3 to 8 kilometers per second, or up to 18,000 miles per hour. Compare that to a regular bullet, which travels slower than 1 kilometer per second, or slower than 2,000 miles per hour. Third, satellites move predictably. There's a strict relationship between the altitude and speed of any object orbiting Earth. Orbital dynamics dictates that satellites at lower altitudes will always travel more quickly than satellites at a higher altitude. Fourth, maneuvers seem slow. And while I said satellites move quickly, because of how big space is, any kind of purposeful maneuver or deviation from their natural trajectory seems relatively slow. And finally, timing is everything. Within the confines of the atmosphere, airplanes, tanks, ships can move nominally in any direction. They can go in a straight line, a circle, zigzag, but objects orbiting Earth don't have that same type of freedom. And consequently, timing for any type of engagement requires extreme precision. And now I'll turn it over to my colleague Jamie Wilson to further discuss the movement of satellites.
Thanks, Becca. One of the most important concepts to understand about space warfare is how to get your space weapon from where it is to where it needs to be. This is known as maneuvering. There are several maneuvers critical for a space war: plane change, altitude change, and phasing. Satellite orbits appear as flat disks with some tilt and some orientation relative to the body being orbited. This is known as its orbit plane. A plane change maneuver occurs when a satellite moves from its current orbit plane to a new one. Altitude changes involve a satellite modifying how high its orbit goes, which can also affect its shape. If a space weapon needs to get close to its target in order to engage, it must match both the orbit plane and the altitude. However, there are only a few places where these maneuvers can occur. Plane change maneuvers can only occur at the 2 points where the planes intersect. Altitude changes are best done at the lowest and highest points in the orbit, which are known as perigee and apogee for satellites orbiting Earth. If a satellite misses these points, it could wait hours before another opportunity arises. Now, just because a space weapon has matched both orbit plane and altitude of its target doesn't mean it's anywhere close to where it needs to be in order to attack. Based on where those previous maneuvers occurred, it could be anywhere in that orbit. What's needed to finish the moving of the satellite into position is known as a phasing maneuver. A phasing maneuver occurs when a satellite changes its altitude just slightly so that it goes faster or slower relative to its original position in the orbit. This moves the satellite along the orbit to where it needs to go. Think of it like trying to pass someone on the freeway. If two cars go the same speed, say 60 miles an hour, their relative velocity is 0. They appear to stay still relative to each other. If the second car speeds up to 70 miles an hour, it will begin to pull away with a relative velocity of 10 miles an hour. A car traveling at 60 miles an hour in the opposite lane has a relative velocity of 120 miles an hour and zips by quickly. Once the satellite reaches its desired position, it moves back into the original orbit. Because the relative velocity differences are small, this can be very time-consuming. To get an idea of how a phasing maneuver works, watch this animation. Here are two satellites in the exact same orbit. An attacking satellite, shown here in red, and a target satellite, shown here in blue. They are 180 degrees away from each other. To catch up, the attacker will begin a phasing maneuver by lowering its perigee and beginning to catch up. However, since the relative velocity differences are small, this process is slow. Nearly a whole day goes by before the attacker can finally catch up to its target. Now you know why Hollywood never shows these maneuvers in their movies. Once an attacker phases itself into position, it can begin what's known as a rendezvous and proximity operation, or RPO. An RPO attack can include the attacking satellite circling its target to take pictures or scan for weaknesses. It can involve grappling onto the target to rip off solar panels or communications antennas or other sensitive equipment. It can even involve releasing other effects to cause problems for the target. Now, all this talk of maneuvering is well and good, but nothing is free. Every time a maneuver occurs, an engine must turn on, and that requires propellant. A satellite's propellant budget is often measured in terms of what's known as delta V, or the amount of velocity change, whether speed or direction, that's available from the propellant load. All satellites are constrained by the amount of delta V that they can carry. As a general rule, larger and faster maneuvers require more delta V than slower and smaller ones. The operators of a space weapon must carefully budget their delta V so that they have enough for all the maneuvers that are required throughout the satellite's lifetime, especially if the space weapon has to go against multiple targets.
Thanks, Jamie. But what does all of this mean for conflict? The maneuvers that Jamie just explained help us to understand how to position a satellite for hostile intent. But just these basics of space dictate that space-to-space engagements will be deliberate, with spacecraft maneuvering days, if not weeks or months in advance to get into position to have meaningful operational effects. However, a satellite does not have to be close to its target to be a threat, and their non-intuitive motion allows for unique approaches for attack. The primary kinetic threat is an anti-satellite weapon, or an ASAT. They can be launched from other satellites, called a co-orbital ASAT, or they can be launched from the ground, more like traditional missiles. Here we show 3 different examples of ASAT collisions. First is a ground-launched ASAT producing a head-on collision. This is the highest relative velocity of the 3 that we'll show, and also offers the least amount of time for any course corrections. Second is a co-orbital ASAT with a tail-on collision. This does allow for more time to adjust, but also has a slower relative velocity. And finally, another co-orbital ASAT with a T-bone collision. This has a high impact velocity and little time for course correction. This is also what the Iridium Cosmos accidental collision was in 2009. However, kinetic attacks have consequences which are relevant both for further engagements during a particular conflict, as well as for the future of the space environment. This animation shows the generation of a debris cloud from a head-on collision. Recall, satellites move very quickly, thus a small piece of debris, even the size of a penny, could destroy a satellite. In just a matter of hours, the debris cloud begins to wrap around Earth. And how long that debris cloud lasts and stays in space before burning up in the atmosphere depends on the altitude of the collision. Not all threats are kinetic, as Jamie will explain more in this next section.
Kinetic attacks certainly sound exciting, with the explosions and the destruction and all of that good stuff. But sometimes you want a subtler form of war, one that doesn't involve getting too close to your target. One way to do this is through electronic warfare. A common technique in electronic warfare is known as jamming, which involves flooding the communications links of a satellite with a bunch of random noise, much like a modern music concert. The goal of a jamming attack is to prevent critical messages, such as mission data or commanding links, to get to where they need to be. Another technique, known as spoofing, seeks to mimic the signals that a satellite should be expecting to see to cause the satellite to do things it wouldn't normally do. Both jamming and spoofing attacks are known as reversible attacks, which means that the satellite is not permanently damaged. This is useful in a low-intensity warfare situation, where you don't really want to blow your cover or you want to maintain some plausible deniability. Directed energy attacks involve using lasers, high-power microwaves, and other waveforms to disrupt normal satellite operations. Now, when we think of lasers, we instantly conjure up images of huge theatrical explosions in space or villains expecting heroes to die under bright blazing beams. But in reality, there wouldn't be such dramatic results. A laser would commonly be used to temporarily blind or dazzle an imaging satellite to prevent it from taking pictures. For more permanent effects, lasers and high-power microwaves could be used to target onboard electronics, thus leading to a satellite's early demise. Satellites that are disposed in this way would remain fairly intact and would leave few clues as to whether its death was caused by an internal problem or by an external attack. Electronic warfare and directed energy attacks offer many advantages over kinetic weapons, the most prominent being that they're not used up after one shot, but can be used again and again to engage many satellites over the course of a campaign. Also, because electronic warfare has been used in modern wars for many years, these effects can be more greatly appreciated by terrestrially minded military leaders who can naturally see the extension of these Earth-based effects into space. One drawback of electronic attacks is that the strength of the signal dissipates the further out it goes. And because space is big, there's a lot of distance a signal must travel before it can reach its target. This animation shows how much that signal dissipates while it goes through space to its target. An attacking signal is only 1/trillionth its starting power by the time it reaches its target, due only to distance losses. When we consider atmospheric absorption, it loses an additional 90% on top of that. And a space-based attacker trying to reach a satellite close to Earth will have its signal go through twice the atmosphere, leading to even more losses. Thus, a successful electronic warfare or directed energy attack requires huge amounts of power to be successful, which places constraints on how small or how far away a weapon can be placed.
Hopefully by now you can tell that a space war would not be quite as intense and action-packed as Star Wars and other movies and TV shows would have you thinking. Instead, it would be fairly slow and deliberate, and probably will not involve humans, at least not anytime soon. Remember to keep those 5 key points in mind. Space is big, satellites move quickly, but they also move predictably, and those points combined mean that satellite maneuvers slowly, and finally, timing is everything. For more details on this topic, see our paper at aerospace.org/policy. Thanks.